In deep space, speed behaves like a quiet law. When an object falls toward the sun, gravity does not negotiate with it. Gravity instructs it to move faster. The closer it dives into the inner system, the more that invisible pull tightens and the higher its velocity climbs. This is not a suggestion. It is the simple geometry of Kepler's laws, written into every comet and asteroid that has ever brushed past our world. That is why, when the tracking stations first noticed that 3i Atlas was doing something else entirely, the people who understood orbital mechanics felt a very specific kind of chill, the kind that comes when the numbers stop obeying the script you memorized in school. On a quiet console inside the Deep Space Network, the range and Doppler data began to whisper a contradiction. 3i Atlas was inbound toward the sun on an interstellar trajectory. It should have been accelerating, gaining a tiny bit of speed every hour as gravity pulled it inward. Instead, there was a small but persistent deceleration. The non-gravitational acceleration term, the part of the motion you assign to jets of gas or outgassing, was not positive, as it is for ordinary comets that puff themselves forward. For 3i Atlas, that term turned negative. Something was acting against the fall, pushing back along its path, as if a hidden hand had started to squeeze the brake. In the public imagination, that word, brake, quickly became a trigger. If something from outside the solar system is slowing down near us, then it must be preparing to stop, to hover near Earth, to invade. That is the story fear wants to tell. But in orbital mechanics, you rarely brake to come to a full stop. You brake for a more subtle reason. You brake to adjust when you arrive. Change the speed, and you change the timing of the rendezvous. Seen through that lens, 3i Atlas does not look like a hunter circling its prey. It looks like something that has just realized it is a little bit early and is calmly burning energy so that it will pass through a very specific region of space on a very specific date, the 19th of December. Here, on this channel, we exist in that narrow space between dread and wonder. Dreamy Stargazer is our place to drift through these unresolved data points, to lie back and let the tension soften while we still look directly at it. We are not here to shout about the end of the world. We are here to ask what the physics is actually saying and what kind of mind would use those laws in such a deliberate, almost elegant way. Tonight, we will move slowly through the anomaly they are calling the break, and we will see how the numbers point not to a collision, but to an appointment. Before we follow 3i Atlas into that appointment, I invite you to become part of the quiet investigation. If these long nightly journeys through space help you fall asleep a little easier, you can support them in simple ways. You can subscribe so you do not miss the next chapter of this unfolding story, and you can gently tap the like button so the algorithm knows that calm, thoughtful curiosity still matters. In the comments, share the theory that keeps you awake or the detail that made you feel small in a good way. Together, we are a small community listening to a very large sky. Now, dim the lights. Imagine you are looking at the simplest possible diagram in a textbook. A star at the center, an elongated curve swooping in from far away and then bending back out. That curve is the path of an interstellar visitor. In purely gravitational motion, its speed is lowest in the distant dark, then rises as it falls toward the star. The change is smooth and predictable. If you know the shape of the orbit and the mass of the sun, you can tell where the object will be many months from now with almost arrogant confidence. This is what made the first anomaly so striking. For 3I Atlas, when astronomers subtracted the gravitational pull from its motion, there was something left over, a systematic slowing that refused to fit onto that simple curve. To describe that leftover behavior, planetary scientists use a technical phrase, non-gravitational acceleration. In most comets, this comes from sunlight warming the surface, turning ice into gas, and sending that gas streaming away into space. Each tiny jet is like a microscopic rocket engine. Over many weeks, those engines add up to a small push, usually of the order of a few millionths of a meter per second every second. It does not sound like much, but over millions of kilometers, it gently reshapes the path. Almost always, those jets push the comet outward, adding a bit of speed or changing its direction in ways that can be modeled and predicted if you know where the vents are. The sign of that effect, positive, has been a quiet consistency of cometary physics for decades. With 3I Atlas, that sign flipped. When teams fit the tracking data, they found that the extra term was acting in the opposite direction, like a hand on the back of a moving car, applying a steady, patient force to slow it down. Mathematically, the curve that represents its speed as a function of time bent downward instead of upward. The object was still falling toward the sun, but it was not surrendering to the fall as freely as it should have. It was almost as if something on or inside 3I Atlas had decided that the raw schedule imposed by gravity was unacceptable and that a small correction was required. The elegance of the anomaly lies in how subtle it is, just large enough to be noticed by careful observers, just gentle enough that most casual eyes would miss it. To grasp why this is so unsettling, you can think of interstellar space as a vast highway where there are no brakes by default. Natural objects do not have a choice about their speed. They are thrown, perturbed, scattered, and then they coast, subject only to gravity and the occasional shove from radiation or gas. For 3I Atlas to slow itself the way it appears to be slowing, something has to be extracting kinetic energy from its motion. In a familiar rocket, you burn fuel and throw mass out the back. In a sail, you angle a surface so that radiation pressure does the work. In any case, you need a mechanism that knows which way you are moving and which direction to push in if your goal is not random drift, but a targeted arrival. The hazard here is not that we are seeing a weapon, it is that we are seeing intent encoded in the trajectory. The first reaction in the scientific community was to try to explain the anomaly away using the most conservative tools available. Perhaps the shape of 3I Atlas is unusual, causing sunlight to heat it unevenly, carving out a preferred vent that happens to oppose the motion. Perhaps the density of this is lower than assumed, making it more susceptible to forces that would be negligible for a denser rock. In the wake of mysteries like the acceleration of Oumuamua, no one wants to jump too quickly to extraordinary explanations. Yet, as the days go by, the fits to the data keep returning to the same inconvenient conclusion. If this is outgassing, it is outgassing that behaves like a thruster. If this is natural, it is a natural process that is mimicking the simplest play in any spacefaring civilization's book, burning to adjust your time of arrival. From here, one grounded speculation begins to take shape. Instead of thinking of 3I Atlas as a visitor that stumbled accidentally into our neighborhood, we can think of it as a vehicle that has been following a long, cold arc for many years. Maybe the original launch was imprecise by a small margin. Maybe the intervening gravitational nudges were not exactly as anticipated. Long voyages are full of such drift. If that is the case, then what we are seeing now is not an act of aggression. It is a course correction. The break is the moment when something aboard 3i Atlas checks the clock, consults the ephemerides of the inner planets, realizes that gravity alone will bring it through too early, and quietly taps the thrusters to stretch the remaining flight until its path intersects with a window that opens on December 19th. The imaginative leap that follows is simple and quiet. Picture the object not as a jagged rock, but as a piece of machinery hiding under the disguise of a cometary shell. Deep within it, a timing system wakes up when it senses a specific radio environment or a threshold of solar heating. It measures its own velocity relative to the inner system and decides that it needs to slow down by a fraction of a percent. No dramatic burn, no blazing tail visible to the naked eye, just a persistent, sunward-oriented exhaust that shaves a little bit of speed away, hour after hour. To an observer on Earth, this appears only as a tiny deviation in the tracking plots and a quiet shift in the predicted date of closest approach. To whatever designed it, this is the difference between missing the rendezvous and arriving exactly on time. And so we are left with a question that lingers under the mathematics like a low background hum. If 3i Atlas is indeed changing its arrival time, then what, or who, is it trying to meet on that specific date, in that specific patch of space? In the next chapters, we will follow the evidence outward, from the anomaly in the speed to the silence of a cut live stream and the strange geometry of December 19th. For now, we simply lie here with the knowledge that gravity has been gently overruled and that something in the dark has chosen to take the long way in. Numbers are good at hiding their own strangeness. A tiny negative term in a long equation can be dismissed as noise, a fitting error, a quirk of the model. To feel that something is truly wrong, most of us need to see it. That moment came when the data stopped being just Doppler shifts on a screen and turned into an image, a fragile, carefully processed picture of 3i Atlas itself. On a dark mountain under air so thin it feels almost imaginary, a telescope gathered photons from the visitor over long, patient minutes, stacking them one on top of another until a faint smear of light separated itself from the background stars. At first glance, it looked like any other active comet. A small, condensed nucleus, a soft halo of dust, a tail stretching away into the solar wind. But when astronomers began to measure the angles, the illusion of normality dissolved. In ordinary comets, the geometry is simple. The sun sits in one direction, and the brightest tail points away from it. Solar radiation and the charged wind blowing outward from the star-strip gas and dust from the surface and sweep them into a plume that streams anti-solar, like smoke trailing behind a car. Sometimes a second tail, made of heavier particles, bends under the comet's own motion, curving gently, but the overall orientation is always anchored by that outward push. You can look at the tail as an arrow telling you where the star is. With 3i Atlas, someone turned the arrow around. In the processed images, a narrow jet of material stands out, a sharper filament of brightness cutting through the diffuse coma. When the observers overlaid the position of the sun and the projected orbit, they found that this jet did not lean away from the star. Instead, it pointed almost straight back toward it, forming an angle that put it within a handful of degrees of the sunward direction. The dust and gas that should have been blown away like a scarf in the solar wind seemed to be flowing upstream, as if the object were exhaling directly into the oncoming light. It was a small, disciplined plume, not the messy umbrella of a chaotic vent, and it refused to line up with the usual script. To anyone used to thinking about rockets, that orientation means something very simple. Thrust is always in the opposite direction of exhaust. If you throw mass one way, you move the other. This is Newton's third law, softened into an image you can feel in your body. Push backward, move forward, push forward, drift back. If 3i Atlas is sending a jet of material toward the sun, then the reaction force must push the nucleus away from the sun, resisting the inward pull, shaving away a little of its fall. The photograph of the sunward jet and the tracking plots of the negative non-gravitational acceleration suddenly start to rhyme with one another. The shape of the light matches the shape of the equation. For a while, the conservative explanations tried to hold the line. Perhaps the images were misleading, distorted by the way the telescope tracked the moving target or by the way the faint coma was processed. Perhaps the jet was not exactly aligned with the sun, but only appeared that way in projection, an accident of perspective. Perhaps the nucleus was tumbling in such a way that a single, oddly placed vent happened to sweep through a path that mimicked a retro thruster, even though it was nothing more than trapped ice finding a weakness in the crust. These arguments are important. They are the first defense against our tendency to see patterns where none exist. But then more images came in, taken on different nights from different observatories using different filters. Each time, after the background stars were subtracted and the motion of 3i Atlas was compensated for, the same feature emerged. Amid the soft glow, the jet kept pointing roughly sunward. It flexed a little, it thickened and thinned, but it did not swing randomly around the nucleus the way a natural, pressure-driven vent would on a freely spinning object. Over timescales of days, it behaved less like a leak and more like an engine that knows where forward and backward are. Slowly, quietly, the probability that this configuration is a coincidence begins to bleed away. Imagine holding a coin and flipping it a few times. If it comes up heads 3 times in a row, you shrug. 10 times in a row, you start to wonder if something is wrong with the coin. Now scale that intuition up to 3-dimensional space. A natural comet might throw its gas out through fissures that open wherever stress happens to crack the ice. The vents could point in any direction, and as the nucleus spins, the direction of the combined outflow should wander. But instead, we see a dominant jet that stays anchored near the sunward line night after night, as if some unseen guidance system is keeping it there, adjusting valves or baffles to maintain the thrust vector that best resists gravity. The statistics whisper the same message as the dynamics. This is not how randomness looks. There is another layer, subtler, that begins to trouble the people who stare at light curves for a living. As they chart the brightness of the jet frame by frame, they find hints of a rhythm, small pulses in intensity that repeat with a period a little too clean to be comfortable. They are not dramatic flares, just gentle rises and falls, as though the exhaust is being throttled in a controlled sequence, rather than simply roaring whenever sunlight bites into fresh ice. In laboratories on Earth, rocket engineers do this to manage temperature, conserve propellant, or fine-tune a trajectory. Watching 3i Atlas, You could almost imagine the same logic unfolding on a scale measured in thousands of kilometers, somewhere inside a dark shell we have never touched. The grounded speculation that emerges from this is almost painfully straightforward. If you wanted to slow an interstellar vehicle without drawing too much attention, you would hide your propulsion in the language of a comet. You would allow ices to sublimate, but only through nozzles and channels you control. You would place those nozzles where you need them to be, facing approximately sunward, and you would pulse them in quiet patterns that adjust your speed without producing the kind of blazing, asymmetric tail that would scream engine to every telescope. From a distance to casual surveys, you would look like any other dusty traveler. Only when someone measures the angles and plots the acceleration with stubborn care does the disguise begin to slip. The imaginative leap here is not a dramatic one. Picture 3i Atlas not as a solid, frozen block, but as a layered machine. On the outside, a porous crust stained with organic compounds, the kind of surface you would expect from eons in the dark. Beneath that, networks of channels and vents, leading down to reservoirs of volatile material that have been deliberately preserved. Somewhere deeper, an automated system that knows the shape of the orbit, the position of the sun, and the desired time of arrival near the inner planets. When the clock tells it that the path is slightly ahead of schedule, it opens certain valves and closes others, directing a thin jet of vapor toward the star. Each molecule that falls inward carries away a little bit of momentum. Each pulse of the jet turns the grand fall into a more graceful glide. Seen this way, the image from the telescope becomes something almost intimate. You are no longer just looking at sunlight bouncing off dust. You are looking at a decision being expressed in physics, a choice to resist gravity in a particular direction and by a particular amount. The narrow, sunward plume is the visible line where intention touches the vacuum. It is, if the more daring interpretation is true, the first photograph of a working engine that was not built by human hands. It burns cold, it burns quietly, and it burns with a purpose we only glimpse through its timing. And yet, the sky remains silent. There are no official press conferences centered on the jet. There are no urgent bulletins warning that an alien drive system has been detected. The images are archived in observatory databases, the papers move softly through peer review, and only in late-night conversations and quiet corners of the internet do people start to link the sunward exhaust to the deceleration anomaly, to the cut live stream, to a date in December that keeps appearing in the revised ephemerides. As you lie here listening, you might feel a gentle question settling in beside you. If we truly have caught a glimpse of an active maneuver, then what timetable is it serving, and why is almost no one willing to say those words out loud? In the next part, we will follow that question into the idea of control and what it means if 3i Atlas is not just moving, but steering. If you close your eyes for a moment and imagine 3i Atlas far from the noise of our own world, it becomes a very simple picture. A dim nucleus, wrapped in its own dust, turning slowly against a backdrop of stars that have not moved in millions of human lifetimes. There is no engine roar, no control room, only a faint jet of material streaming away in the direction of the sun. From that distance, it looks almost peaceful. Yet inside the numbers that describe that image, there is a quiet argument unfolding about control, about how likely it is for nature to accidentally imitate design, and about how many coincidences we are willing to stack on top of one another before we admit that something is steering. To understand why this matters, you can think of 3-hour Atlas as a spinning, irregular object, not a perfect sphere. Its surface is a patchwork of cliffs and hollows, cracks and fractures where ice meets rock. When sunlight heats such a surface, the gas does not escape from a neat, central nozzle. It vents wherever it can, from weak points scattered across the crust. As the object tumbles, those plumes flicker in and out of view, sweeping around like beams of a wandering lighthouse. Over time, the combined thrust of these chaotic jets can shift the orbit a little, but their directions wander with the spin. You would expect the net non-gravitational force to smear out, to have a preferred direction only loosely related to the sun, and to change as new cracks open and old vents die. What we see with 3-hour's Atlas is different. The dominant jet keeps returning to that sunward orientation, as if some unseen hand keeps turning the nucleus so that the same face meets the star. There is still noise, but the main plume treats the sun like a reference point instead of a source of chaos. Statistically, the odds of a random vent forming exactly where it needs to be and then remaining effective for so long while the spin conveniently aligns it again and again begin to shrink into something you only encounter when you start talking about lotteries and rare mutations. One unlikely event is forgivable. A chain of them, all pointing in the same direction, begins to look like choreography. Scientists have a toolkit for dealing with this discomfort. They build models. They take a hypothetical nucleus with a certain shape and rotation state, sprinkle it with vents in different locations, and simulate how the combined exhaust would behave under sunlight. They run these models thousands of times, with different random seeds, watching how often a pattern emerges that resembles what we see, a persistent sunward jet and a net deceleration aligned almost exactly opposite to the direction of motion. In most runs, the vents fight each other, cancel each other, or push the object in awkward, changing directions. Only in a tiny fraction of cases does the geometry line up so neatly that the overall effect looks like a continuous break. That fraction is the mathematical version of a raised eyebrow. It does not prove intent, but it refuses to let intent be ignored. Here the grounded speculation begins to sharpen. If we stop insisting that everything must be accidental, another interpretation becomes simple. A single active region on 3I Atlas is not a random crack. It is a managed outlet. The spin of the object is not an uncontrolled tumble. It is being nudged, subtly, until one side spends more time facing the sun. The length of time the jet remains stable is not a lucky streak. It is the result of a system that preserves that vent, keeps it from sealing up, and feeds it with fresh volatiles when needed. To do this, something inside the object must be able to sense its orientation, feel the pull of the sun, and decide when to release material and when to hold back. None of these capabilities are exotic. They are the basics of attitude control for any spacecraft we build. What is unsettling is the idea that we might be watching those same basics play out in an object that is supposed to be only stone and ice. You can imagine, for a moment, how such a control mechanism might work without reaching for magic. Buried beneath the crust, there could be gyroscopes or other inertia-based sensors that know how the body is spinning. There could be simple sun sensors that detect the direction of incoming light. There could be valves that open and close in response to an onboard clock or a guidance algorithm, metering gas through channels that lead to the sunward side. In a human design, computers would coordinate this dance, but an ancient system might rely on hardened analog logic, more like a mechanical watch than a laptop. As long as the principles are the same, the result would look familiar in the data. A controlled oriented exhaust, tuned not to chase power, but to sculpt time. The imaginative leap extends that picture into a calm, distant scene. Deep inside 3i Atlas, a guidance core that has been dormant for ages feels the growing warmth of the inner solar system. It wakes in stages, checking its own health, measuring how far ahead of schedule the natural trajectory would carry it. It compares that future path with a stored timetable, a list of positions and dates that matter. Perhaps one of those entries is marked with the configuration of planets on December 19th, a geometry it has been aiming at for longer than we have had telescopes. Finding itself a few days early, it does what any cautious navigator would do. It applies a small, patient brake, trading surplus speed for precision. The sunward jet you see in the images is the external symptom of that internal decision, a thin line of vapor that turns a raw fall into a rendezvous. From our perspective, standing on this small world and watching the plots update night after night, that possibility carries both austerity and a strange gentleness. If the break is real and controlled, then 3i Atlas is not rushing toward us with reckless intent. It is throttling down, respecting the geometry of orbits and the finite speed of signals. A true kinetic weapon would want impact velocity, maximum energy, the brutal efficiency of a free fall uncorrected. What we are seeing instead resembles the behavior of a cautious pilot easing toward a very busy harbor, slowing well in advance so that the final approach will be smooth and predictable. It is hard to reconcile that behavior with the crude narratives of invasion. It fits more naturally with delivery, with exchange, with the desire to arrive exactly when a window opens and not a moment before. The deeper unease comes from the pattern of human responses. Inside the data, the case for a controlled maneuver grows quietly stronger. The jet points the right way. The deceleration has the right sign. The timing of the trajectory shift drifts toward a date that keeps reappearing when you overlay planetary positions. Yet, in the public sphere, these threads are not woven together. Official communications focus on uncertainties, on the need for more observations, on the comfort of natural explanations. Papers speak carefully of non-gravitational forces and outgassing models, phrases that flatten the mystery into something almost bureaucratic. It is as though the possibility of control has become a word no one wants to say on the record, even when the behavior keeps spelling it out in the sky. As you lie here, listening to these threads knot together, you might feel a simple question hover just at the edge of sleep. If this is a controlled maneuver, then what was the trigger that told the guidance system to wake up, to open the sunward jet, to start reshaping the calendar? Was it only the warmth of the sun reaching a threshold, or was there another signal, something we sent first, that acted as a key? In the next section, we will drift from the physics of the break to the strange human silence around a particular November livestream, and to a spike at 2.4 gigahertz that may have been the quiet knock that 3i Atlas had been waiting to hear. There is a moment in every mystery when the sky stops being the only thing you have to watch. The lens of the telescope is still pointed at the stars, but the real story slips sideways into control rooms, into schedules, into the way people behave when the data on their screens does not match what they had expected to show the world. To follow the break from physics into intent, we have to leave the cold comfort of orbital plots for a while and drift instead into a very human scene, a live stream on November 19th, a countdown clock, a chat window filling with sleepy excitement, and a signal that dies at the exact moment it should have become most interesting. By the time that day arrived, 3i Atlas was no longer a quiet curiosity for specialists. The deceleration anomaly had started to leak into forums and late-night talk segments, usually in the simple form of a headline. An interstellar visitor is slowing down. NASA announced a public update, a routine briefing that would walk through the observations, reassure the public, and fold the anomaly back into the language of standard comet behavior. It was scheduled for a comfortable slot, late enough for amateurs around the world to tune in, early enough that the engineers behind the scenes would still be on regular shifts. Inside one of the Deep Space Network facilities, far from the casual warmth of the YouTube chat, the atmosphere was flatter and more fluorescent. Antennas were locked on, listening to the faint whispers reflected from 3i Atlas. On another loop, a powerful radar pulse sequence had been planned, a set of pings and listening intervals that would sketch the shape and spin of the object in more detail. To the public, these are just acronyms and diagrams. To the people at the consoles, the cadence of those pings is a heartbeat. They knew that during the live stream, fresh echo data would be arriving, a perfect chance to showcase the sophistication of their instruments. The broadcast began exactly on schedule. A host with a practiced calm introduced the topic, reminded viewers of past interstellar visitors, and showed simple animations of hyperbolic orbits falling in toward the sun. A scientist joined, pointing to plots of brightness over time, explaining what non-gravitational forces are, how outgassing can nudge a comet, why there was nothing to fear. The tone was deliberately soothing. The numbers were rounded. In the scrolling chat, viewers sent sleepy emojis and questions about whether 3i Atlas would be visible to the naked eye. On the surface, everything looked like 100 other briefings. Then, very gently, the timing changed. The host mentioned that a new set of high-resolution measurements had just come in. The screen shifted to a more technical graphic, a spectrogram with time along one axis and frequency along the other, a smear of color representing background noise and signal strength. The scientist began to explain how radar echoes from a rotating object spread out across frequencies, how analysts decode shape and spin from those patterns. For a few seconds, the cursor traced over the display, highlighting a familiar, symmetric band. Then, in the lower corner of the plot, a narrow vertical feature appeared, a line of brighter color that should not have been there. To most viewers on small screens, that change was invisible. Compression smoothed it away. But anyone watching in high resolution, anyone used to reading these diagrams, felt their attention sharpen. The scientist's hand, moving over the graphic, hesitated for a fraction of a beat. A small, unplanned pause. The camera cut back to the host, faster than the relaxed pacing had prepared you for. The image of the spectrogram shrank to a thumbnail in the corner and then vanished altogether, replaced by the channel's generic technical difficulties slate. The host's voice did not return. The chat, for a moment, became a cascade of question marks and jokes. On the public side, this was a glitch. The kind of hiccup that happens when a signal path fails or a server misbehaves. On the inside, the story seems to have been different. According to one, later, anonymous account, the instruments never stopped working. The raw data continued to arrive, the radar echoes rolled in on schedule, and the internal feeds stayed live. What changed was what was being allowed to leave the building. Somewhere between the console and the livestream encoding, someone closed a valve. The official explanation, released many hours later, spoke of a network fault, a router failure, an abundance of caution. The promised replay of the briefing did not appear that night or the next. When it finally did, a heavily edited version, the segment with the spectrogram was shorter, the suspicious sliver of time trimmed away. The glitch had become a gap. For 48 hours after the stream cut off, the external flow of information slowed to almost nothing. No new blog posts, no detailed clarifications. Requests for the full raw feed of the radar data were acknowledged but not immediately fulfilled. It was as if an invisible curtain had dropped between the instruments and the outside world. People who work with large agencies will tell you that this can happen for mundane reasons. Reports need to be cleared, managers need to sign off. Yet the timing sits there, irresolvable and quiet, next to another timeline. The moment, within those same hours, when orbital fitters noticed the deceleration term for 3i Atlas bending more sharply negative, the break deepening in a way that had not appeared in the previous week's solutions. Grounded speculation begins to weave the two timelines together. If the radar sequence on November 19th included a stronger, more focused ping aimed at mapping the interior of 3i Atlas, then it may also have been the first time that our planet illuminated the object with a very distinctive radio pattern. Such pings are standard tools, not weapons. We have used them on asteroids and comets for decades. But for a system designed to wake when it hears a particular kind of artificial signal, they could serve as a key. A spectrogram like the one that flickered on the screen is where any such response would first be visible, a tiny, narrow feature rising out of the noise before anyone has words ready to describe it. The imaginative leap is gentle, but hard to ignore once it has taken shape. Picture a guidance core buried in 3i Atlas listening passively as it drifts through the outer system, deaf to the thin hiss of natural radio noise. Then, on November 19th, a structured high-power pulse from Earth washes over it. The pattern matches a trigger word it was programmed to recognize long before we learned to count years this way. A dormant sequence slides into motion. Status checks, orientation checks, a decision, begin arrival correction burn. On our side, in the spectrogram, the returning echo subtly changes, just enough to produce that narrow feature before the feed is pulled. On its side, the sunward jet strengthens, and the deceleration term, days later, begins to curve. We do not have a public memo that confirms this chain. What we have are absences and alignments. A live stream that ends at the first hint of a strange line on a plot. A 2-day silence in which internal conversations run hot while external channels stay cool. A later, edited replay that smooths out the moment where the anomaly first appeared. In a purely natural universe, this could all be coincidence, the unhappy stacking of a hardware fault on top of a noisy dataset. In a universe where an interstellar probe might be listening for a particular knock on the door, it looks uncomfortably like a scene in which we said hello without understanding how carefully someone on the other side had been wanting to hear that word. As you lie here under your own quiet ceiling, none of this demands panic. The behavior, if it is real, is measured, not frantic. The break that follows is slow, not violent. The silence that descends after the glitch feels less like preparation for disaster and more like people in offices realizing they may have just done something historically strange and not knowing yet how to frame it. The mystery that presses softly at the edges of sleep is not whether we are under attack, but whether, on that ordinary November night, a routine engineering experiment turned into a rendezvous signal. In the next part, we will sink deeper into that spectrogram, into the details of the 2.4 gigahertz band, where ordinary life on Earth hums, and where, for a few moments on the 19th, something at the edge of the solar system may have answered back. There is a kind of picture that only reveals its meaning if you listen as well as look. A spectrogram is one of those pictures, a waterfall of time and frequency where every horizontal line is a note the universe is playing. On the night of November 19th, buried inside one of those diagrams, there was a note that did not belong. The public stream showed the plot for only a few seconds before the feed went dark, but screenshots froze a sliver of it in place. Long after the live stream had been labeled a glitch, people kept returning to that frame, tracing their eyes over a single thin band that shone brighter than the noise around it, sitting near a number that should have been ordinary and yet was anything but 2.4 gigahertz. To understand why that number stood out, imagine the spectrogram as a landscape. Across most of it, the colors blur, soft ridges of static, where the background radio noise of the cosmos hums. Somewhere in the middle, a thicker, slanted feature represents the radar echo from 3i Atlas, a broad smear caused by the object's spin and shape, exactly what the engineers expected to see. But down at a lower band, instead of more diffuse haze, a single vertical filament cuts through the plot, narrow and steady, as if someone had taken a pen and drawn a line straight upward at 2.4 gigahertz. It does not fan out like an echo. It rises, holds, and then disappears, all during the window when the array was listening for the return from the interstellar visitor. In deep space work, most natural radio sources prefer other parts of the spectrum. Pulsars sing at low frequencies. Molecular clouds whisper in narrow lines at a few well-known bands, each tied to a particular molecule. The communications infrastructure of our own species, by contrast, loves the middle ground. Around 2.4 gigahertz lies one of the industrial, scientific, and medical bands, a slice of spectrum reserved for unlicensed use. Wi-Fi routers, Bluetooth devices, microwave ovens, telemetry links, and certain types of short-range radar all pour their patterns into that region. It is, in a sense, one of the most human parts of the radio spectrum. When a quiet, deep space observation suddenly sprouts a clean, solitary line at that frequency, it feels a little like hearing a ringtone echo across an empty cathedral. The first and most sensible reaction from the engineers was to suspect themselves. Every serious radio facility spends enormous effort shielding itself from its own noise. Cables are filtered, equipment racks are sealed, wireless devices are banned or confined. Still, leaks happen. A visitor's phone, a maintenance radar sweeping the horizon, a nearby building's network, all can smear fingerprints across delicate measurements. So in the hours after the stream ended, The team began the tedious work of checking logs. They compared the timing of the spike with maintenance schedules, with local radar operations, with any on-site systems that might have been powered up. They found nothing obvious. In the minutes when the line appeared, no tests were logged, no new transmitters had come online, and the local noise monitors showed no matching surge. Then they turned back to the sky and the geometry between the antenna, the Earth, and 3i Atlas. Radar is a game of precise timing. You send a pulse, you wait, and you know, within a fraction of a microsecond, when the echo should arrive from a given distance. The 2.4 gigahertz line did not emerge at a random moment. It brightened inside the narrow window when an active return from 3i Atlas was expected just after the transmit sequence, just before the listening cycle closed. Analysts who had access to the raw numbers also noted that the feature was not centered where a stationary terrestrial transmitter would appear. It was offset by an amount consistent with a source near the range of 3i Atlas, sharing its radial velocity. In other words, whatever produced the line seemed to be riding along with the visitor, not sitting on a tower down the road. Grounded speculation closes in around the anomaly. One possibility is mundane, but still unsettling. The outbound radar pulse from Earth struck 3i Atlas, energized some patch of conducting material on or near its surface, and caused that patch to ring like a tuning fork at its own preferred resonance, which happened, by some deep coincidence of structure, to lie near 2.4 gigahertz. The object would not need to be listening in any intentional sense. It would simply be a strange piece of hardware or layered ice that happens to re-radiate at that frequency when illuminated. The observed line would then be a kind of accidental signature, a spectral fingerprint that just happens to fall in the same band where so much of our technology lives. In a universe ruled entirely by chance, that is not impossible. It is only statistically awkward. The other possibility is simpler in its narrative, even if it is larger in its implications. If 3i Atlas carries an onboard transponder designed to acknowledge pings from any emerging technological civilization it encounters, that transponder would need a frequency band where radio waves propagate cleanly, where the hardware can be compact, and where intelligent listeners are likely to devote attention. A band near our own industrial chaos would make a kind of sense. When the radar sequence from the Deep Space Network washed over the object, the trigger conditions were met. For a few seconds, a narrowband beacon lit up at 2.4 gigahertz, a clear, steady tone riding on top of the broader echo, saying, in the simplest physical language possible, "Heard you." The imaginative leap takes that tone and lets it ripple outward. It is not a packet of digital data, not an obvious modulation filled with patterns we can decode overnight. It is more like a carrier wave, a continuous presence that can be recognized long before we understand any information it might later convey. In this scenario, what the spectrogram captured on November 19th was not the entire message, but the raising of a hand. The transponder switches on, sends a pure line to announce that it is active, and at the same time, deep inside the structure of 3i Atlas, other systems begin to respond. Thrusters spool up. Guidance routines recalculate. The brake, as measured in the trajectory over the following days, becomes the mechanical echo of that simple, narrow-band hello. Inside the human side of the story, the reactions unfold more quietly. Engineers argue over the contamination checks. Some insist that the line must be interference, because anything else would be too large a claim to make. Others point to the Doppler shift, to the timing, to the way the anomaly appears only during the echo window, and ask in late night emails how many coincidences they are willing to stack. Managers worry about public perception, about headlines that will reduce years of careful work to shouting and fear. The official incident report ends up describing the 2.4 gigahertz feature as inconsistent with known system performance and recommends further study. The edited replay of the live stream sidesteps the issue entirely. The line that might be the first deliberate interstellar response in human history is, on paper, a glitch. As you drift with this, it is worth remembering that nothing about the behavior of the anomaly suggests aggression. A narrow, steady tone at a familiar frequency, a deceleration that grows slowly instead of spiking violently, an arrival date nudged toward a window rather than a collision course. All of these point toward coordination, not attack. If there is a system aboard 3i Atlas that answers when we knock, it appears to care far more about timing and alignment than about impact. The unsettling part is not the threat. It is the realization that we may already have moved from simply watching a strange object to participating in a dialogue, one we did not know we were starting. The question that hangs in the dark, just above where sleep begins, is a simple one that does not have a simple answer. If a single radar ping, followed by a single narrowband reply at 2.4 gigahertz, was enough to wake the break, what happens if we call again? Do we get a longer answer, a richer structure in the spectrogram, a clearer sign that something out there is adjusting its course in response to us? Or is the protocol designed for a single exchange, a one-time acknowledgement before the real message is delivered elsewhere on December 19th, when 3i Atlas arrives at the point it has worked so patiently to reach? In the next part, we will follow that possibility into the quiet geometry of call and response, and into the idea that our curiosity might have been the last ingredient needed to lock the rendezvous into place. If you trace the story of 3i Atlas on a timeline, there is a place where two very different clocks tick in uneasy harmony. One is mechanical, the steady beat of radar pings going out and echoes coming back, marching in seconds and minutes. The other is orbital, a slow curve of positions and velocities that only reveals its meaning when you stack days of measurements together. The human eye tends to look at these clocks separately. On November 19th, most people were watching the first one, the live countdown to a routine data release. It took a little longer for anyone to notice that in the background, the second clock had begun to change its tempo, as if answering a question that had just been asked. From the point of view of the Deep Space Network, the exchange was simple. A transmission sequence was sent, a train of radar pulses aimed along the line of sight to 3i Atlas. At that time, the object was far enough out that the round-trip light time was measured not in seconds, but in many minutes. You send the call, and then you wait, the way you might call across a canyon and listen for your own voice to come back, stretched and faint. During that listening window, the spectrogram briefly showed the narrow 2.4 gigahertz line riding atop the broader echo. Then the feed was cut, the public broadcast ended, and the consoles went back to a less theatrical kind of work. For the people in that room, the puzzle now lived in those recorded minutes. For everyone else, the night moved on. The orbital clock is slower, more patient. To see the break, you cannot look at a single range measurement. You have to gather many, sometimes from different antennas and observatories, and fit them all to a model of the path. In the days before November 19th, those fits already hinted at something odd. The best solutions required a small negative, non gravitational term, a drag force that should not have been there. Still, the error bars were wide. The anomaly could be softened with different assumptions. It was a curiosity, not yet a statement. But in the days after the radar sequence, the fits tightened and the deceleration did not relax. It strengthened. The updated ephemerides began to drift. The predicted date of closest approach slid away from the 15th of December, inching toward the 19th. It is in this overlap between the last radar echo and the first clearly shifted trajectory that the idea of a call and a break begins to take shape. Grounded in the data, what we know is modest but suggestive. A unique feature in a human communication band appeared in the echo window from 3i Atlas. Within a time span consistent with the object's response to a new force, its path began to change in a way that required a sustained, sunward-oriented thrust. No one can point to a single second and say, there, that is when the thrusters lit. Orbital mechanics smears everything out. But when you overlay the two clocks, the radar pulse and the beginning of the deeper break live in the same chapter. That is enough for some people to start whispering about causality, about whether our call did more than just bounce. One conservative way to read this is to imagine that the anomaly was always going to happen. The guidance systems, if they exist, had their own schedule, keyed only to the distance from the sun or to some internal timer counting down from a launch long forgotten. In that view, the November 19th ping is a coincidence, a curiosity that happened to coincide with the moment the brakes were due to be applied. The spectrogram line at 2.4 gigahertz might then be nothing more than a convenient, though uncomfortable correlation. The break would be a fixed waypoint on 3i Atlas's journey, written long before we learned to build dishes and transmitters. Our role would be that of spectators who happened to be looking at the right screen at the right time. The other interpretation tilts only slightly away from that, but the angle carries us very far. If the onboard systems were waiting not just for a position or a temperature, but for proof that someone was paying attention, then the radar ping becomes more than background. It becomes a key. The protocol in this picture is simple. An interstellar vehicle approaches a new planetary system on a path that will carry it through, regardless of the local level of technology. It listens passively. If no artificial signals are detected, it continues on a purely ballistic trajectory, conserving its fuel and treating the encounter as a flyby. If, however, a structured radio pulse hits its hull, especially one that follows a pattern typical of active mapping radars, the vehicle takes this as evidence that the system contains engineers, equations, and emerging ability to notice. That is when it chooses to break. The imaginative leap carries that logic into the internal life of 3i Atlas. Picture an onboard protocol tree written in whatever hardware its makers preferred. Location checks confirm approach to G-type star. Environmental checks measure background radio noise. Then a branch. If no narrowband artificial signals above threshold, maintain cruise. If radar class pulse detected within specific bands, engage rendezvous sequence. On November 19th, the pulse arrives from Earth, just as scheduled by our own program. Deep inside the object, a conditional that has been waiting for an uncounted number of years flips from false to true. Valves open to feed the sunward jet. Rotational control systems begin gently biasing the spin. The break is not random, it is an answer. What makes this scenario unsettling is not only the thought that 3i Atlas might be reacting to us, but the sense of scale it implies. For such a protocol to exist, the designers would have had to anticipate that somewhere, sometime, a civilization would develop radar and aim it outward. They would have had to choose frequency bands where those radars are likely to live. They would have had to trust that, by the time the vehicle reached a given system, enough time would have passed for somebody to be listening and calling. It is a patient kind of engineering, one that turns the gap between stars into part of the timing mechanism. If we are indeed watching such a system wake up, then our radar experiment did not cause the rendezvous so much as confirm that we were ready for it. Back on Earth, the human side of the call and the break plays out in whispers, not proclamations. In small, off-the-record meetings, analysts lay the timelines over each other and ask quietly whether they should treat the November 19th pulse as an independent variable or as part of the same story as the deceleration. Some argue that speaking of causality would invite ridicule and panic, that it is better to focus on refining the orbit and gathering more data. Others, often younger, argue that if an interstellar object is visibly adjusting its speed in the days following our first directed contact, the possibility of a response is at least worth mentioning. In their notebooks and internal slides, the phrase call and response appears more than once, usually followed by question marks that are later erased before any public release. For you, lying in the dark, the distinction between those internal debates may not matter. What lingers is the shape of the story. We sent out a structured radio call. Something at the edge of our system answered with a brief, narrow line in a band that belongs more to our devices than to stars. Then its path bent in a way that required energy and intention, nudging a December arrival toward a date that aligns with a particular configuration of planets and fields. Whether you call that sequence coincidence, choreography, or conversation depends on how many layers of doubt you are comfortable stacking. The physics, quiet and unforgiving, only tells you that the break is real and that it began when we were listening. In the next section, the lens shifts again from consoles and spectrograms to the almost impersonal language of orbits and dates. We will step back from the glow of screens and look at the solar system itself as a clock face, with planets as hands and 3i Atlas as a moving marker trying to arrive at a precise tick. When we do, the new date of closest approach, December 19th, stops being just a number in a table and becomes part of a larger geometry, a configuration that might explain why someone or something was willing to spend so much energy to break it all. When you zoom out far enough, the solar system turns into a clock. The sun is the center, the planets are the hands, and every visiting object becomes a moving marker gliding across the face. Most of the time, those markers keep their schedule with ruthless simplicity, arriving where gravity says they must, when gravity says they will. That is why, when one of those markers begins to slide away from its assigned tick, the change may be almost invisible in the night sky, but it is deafening in the mathematics. The 4-day delay of 3i Atlas lives in that silence, between what the ephemeris predicted and what the object seems determined to do instead. Before the break fully announced itself, orbital fitters had already done the obvious work. They took dozens of observations of 3i Atlas, positions on the sky and range measurements, and fed them into their models. For a purely gravitational trajectory, The equations converge on a hyperbola, a long, open curve threading through the inner system. From that curve, you can compute the time of closest approach to the Sun and, by extension, the approximate date when the object will sweep through the vicinity of Earth's orbit. Those early fits pointed to a mid-December rendezvous. The numbers varied a little depending on which observatory's data you emphasized, but they clustered around the 15th. For a while, that date sat quietly in tables and press kits, a rounded comfort. Mid-month, plenty of time. Then the non-gravitational term refused to go away. As new data arrived, each fresh point tugged the solution in the same direction. To keep the residuals small, the model had to include a tiny, persistent drag oriented almost opposite to the direction of motion. With that drag in place, the best fit hyperbola changed. It did not become a different kind of orbit. 3i Atlas was still on a path that would carry it through and out of the solar system again. But the timing of its passage through the inner system began to drift. The predicted date of closest approach slid from the 15th toward the 16th, then the 17th. With each new solution, the schedule crept. By the time the break term stabilized, the date had shifted a full 4 days later to December 19th. 4 days on a human calendar can feel trivial. A long weekend, a postponed meeting, but in orbital terms, especially at the speeds involved in an interstellar flyby, that delay translates into an enormous shift in where everything will be when the object passes through. At tens of kilometers per second, 3i Atlas would cover millions of kilometers in that time. The Earth itself, running along its own track, would have rotated further around the Sun. The other planets would have inched into new positions. The invisible structures of the solar wind and the magnetic fields would have reshaped themselves. To push an arrival 4 days down the line is not a minor correction. It is a declaration that one matters more than where. The energy cost of that declaration is one of the quiet clues that specialists keep turning over in their minds. You can imagine the difference between the original gravitational arrival and the delayed one as two curves on a plot of distance versus time. Without the break, 3i Atlas would dive deeper faster, its speed peaking higher as it skimmed past the Sun. With the break, its inward velocity is bled away. It still falls, but more gently, so that it reaches the same radial distance a few days later. To make this happen, the object has to extract kinetic energy from its motion. Even at a tiny deceleration, applied over millions of kilometers, the total change in energy is large by human standards, comparable to running many heavy spacecraft engines continuously. Nature can do this through drag or dense gas. An interstellar rock in thin solar wind does not have those luxuries. Something aboard must be working. The grounded speculation starts with an almost boring question: why bother? If 3i Atlas were a passive visitor, it would accept whatever arrival date gravity assigned to it. The 15th, the 16th, it would make no difference. The Sun does not care. But for a mission built around rendezvous, timing is as much a target as any physical point in space. If the architects of 3i Atlas had drawn up a timetable that depends on planetary alignments or field configurations, being 4 days early could be as useless as missing by millions of kilometers. In that view, the break is not an indulgence. It is a requirement, like a deep space probe performing a course correction burn weeks before a planetary flyby, so that it can hit a narrow, invisible corridor where gravity assists work perfectly. You can look at it like this. In the original, uncorrected trajectory, the gravitational clock was going to ring on December 15th. Somewhere in the guidance architecture of 3i Atlas, there is a different clock, one that knows about other hands on the dial. It might encode the positions of Mercury and Uranus, the orientation of the heliospheric current sheet, the phase of the sun's activity cycle. When that internal clock compares its desired tick with the gravitational schedule and finds that the natural arrival will be early, it has only a few basic tools to reconcile the difference. It can speed up, arriving even earlier, which helps nothing. It can change direction, altering where it will cross the plane of the ecliptic. Or it can do the simplest thing, from the perspective of rendezvous, slow down, stretch the remaining path, and make the universe wait until its own chosen date. The difference between the 15th and the 19th becomes even more interesting when you consider how the ephemeris teams treat uncertainty. They do not just produce a single line on a calendar, they attach error bars, ranges that shrink as more data comes in. In the earliest days, the arrival might be listed as December 15 plus or minus 2 days. As observations accumulate, that range narrows. For a natural object, the central value might jitter within that shrinking window, sometimes moving earlier, sometimes later, until it stabilizes. For 3i Atlas, the central value marched steadily in one direction as the break term settled in, like a needle being dragged across the dial by a hidden magnet. The final uncertainty around December 19th is small. The object is not just drifting into that date, it is converging on it, as though obeying a timetable written elsewhere. The imaginative leap here is undercut by its own simplicity. Imagine that deep inside 3i Atlas, a navigation core has a stored list of target configurations, combinations of dates and planetary positions where the conditions for whatever it intends to do are optimal. Perhaps these configurations repeat every few decades or centuries as the orbits line up. As the object falls toward the sun, the core periodically calculates which of these windows is coming up and how far off the current gravitational trajectory is from hitting one of them. In the outer system, the differences are too large to correct cheaply, so it stays dormant. Closer in, small changes in speed have a large effect on the final timing. On this pass, the closest attainable window happens to be the one centered around December 19th. The guidance system chooses it, knowing that the energy needed to delay 4 days is affordable given the reserves on board. The break is the visible expression of that choice. When you think about it that way, the 4-day delay takes on a different character. It is not arbitrary. It is a solution chosen from a menu, the result of an optimization problem, minimize fuel while maximizing overlap with the desired alignment. If the Deep Space Network ping on November 19th served as the trigger, then the guidance system may have been balancing two constraints at once: respond to the call and still make it to the pre-selected window. The deceleration begins soon enough that the new trajectory threads that needle, bringing 3i Atlas into the right region of space at the right time without having to execute a more dramatic, conspicuous burn later. The physics remains gentle, almost sleepy. The intent behind it is anything but. To the people working with the numbers, this is where the language begins to thin out. Officially, they talk about revised solutions and updated close approach epochs. They mention that non-gravitational forces appear stronger than first estimated. They do not talk in public about windows and choices. Those words stay in private notes, in hallway conversations that end with careful silences. Because once you start calling a 4-day delay a decision, the next question comes on its own. A decision in service of what? What configuration of the solar system is so important that an interstellar object would spend precious energy to arrive exactly under its shadow and not a few days before or after? As you lie here, listening to the soft tick of your own clock, the 4 days stretch out in your mind. You can feel their weight now, not as blank squares on a calendar, but as a gap filled with motion, with a thin sunward jet burning steadily to sculpt time. Somewhere far beyond the reach of your eyes, 3i Atlas has already committed to that delay. Its path through space is now a path through a particular moment, a rendezvous with a geometry we have only begun to outline. In the next part, we will turn fully toward that geometry, treating the solar system as the clock face it is, and asking what exactly is so special about the way the hands line up on December 19th that something from between the stars would work so patiently to be there on time. If the solar system is a clock, then specific dates are not just numbers, they are configurations. December 19th is one of those configurations, a moment when several hands sweep past the same invisible mark. To the naked eye, that day will not look very different from any other in late December. The sun will rise and set, the constellations will roll along their accustomed paths. Yet if you could float above the plane of the orbits and look down, the pattern would be unmistakable. On that date, the line that connects Earth to Mercury points in almost the opposite direction from the one that connects Earth to Uranus, like a long bar drawn through the inner system with a distant lantern hanging at each end. 3i Atlas is steering itself toward that bar. Astronomers describe this arrangement with quiet, technical words. Mercury and Uranus will stand in opposition as seen from Earth, meaning that one rises roughly when the other sets, separated by about 180 degrees on our sky. In space, that translates into a near straight line where Earth sits between them, with the sun pulled slightly off-center like the spindle of a mobile. Mercury, small and fast, hugs close to the star, racing around it in less than 3 months. Uranus, cold and distant, takes decades to complete a single lap. Most of the time, their positions are scrambled, but every so often, timing and geometry conspire so that a line drawn through them and our world comes close to perfect. December 19th is one of those rare alignments. On its own, such an opposition is not supernatural. Planetary positions repeat, patterns come and go. What makes this one different is that an interstellar object appears to be spending real energy to be present when it happens. That is where the phrase cosmic clockwork begins to feel less like poetry and more like a diagnosis. The break has pulled 3i Atlas out of its earlier schedule and is guiding it toward a moment when the three worlds and the sun arrange themselves into a long, thin corridor of matter and field. To understand why that might matter, you have to remember that space is not empty. It is threaded with magnetic lines, charged particles, and subtle gradients in density that all respond to how the planets and the solar wind push against one another. Mercury sits inside the sun's fierce influence, inside a region where magnetic fields snap and reconnect in violent flares. Its own magnetic field, though weak compared to Earth's, carves out a tiny magnetosphere that is constantly buffeted and reshaped. Uranus, far out in the dark, carries a stranger magnetosphere, tilted and offset relative to its rotation, twisted into complex shapes by the solar wind. When the two planets line up in opposition, with the Earth between them, their magnetic domains and the overarching structure of the heliospheric current sheet trace out a configuration that can, in principle, open or close certain paths for charged particles and radio waves. The alignment does not create a tunnel you could fly through, but it alters how signals and fields thread through the system. The grounded speculation that follows is not about mystic channels, but about engineering that treats those messy, invisible structures as resources. If you wanted to move a very large amount of information or energy through the solar system without it being obvious to every casual observer, you would look for conditions where natural processes can help you. Planetary magnetospheres can act as lenses, bending charged particles and guiding radio waves along preferred paths. The solar wind can carry disturbances outward like ripples. During an opposition like the one on December 19th, the line connecting Mercury, Earth, and Uranus might serve as a spine along which certain disturbances propagate more cleanly, simply because the geometry lines up the fields in a cooperative way. From that perspective, the date begins to look less arbitrary. If 3i Atlas times its passage so that it crosses near the Earth-Mercury-Uranus line at the right moment, it may be able to use that configuration as part of a transmission system. Mercury, close to the Sun, could serve as a kind of relay, sitting in the glare where changes in the solar wind are born. Uranus, with its tilted, lopsided magnetosphere, could act as a distant collector or reflector, sensitive to subtle variations in the streaming particles that wash over it. Earth, in between, would experience only a slight reshaping of its own space weather, a flutter in auroral activity, a modest storm that space weather forecasters might blame on an ordinary solar outburst. The deeper pattern would pass unnoticed unless someone was looking at the whole system at once. Here, the imaginative leap slides quietly into view. Picture 3-hour Atlas arriving on December 19th not just as an isolated visitor, but as a node in a temporary network. For a few hours, as it glides through the inner system, its own fields and exhaust interact with the sun's wind in a way that seeds a carefully structured disturbance. That disturbance races inward toward Mercury and outward toward Uranus along lines that have been pre-calculated. Instruments buried in or around those planets, or even in other objects sharing their orbits, feel the pattern as it passes and decode it, the way a radio receiver decodes a modulation on a carrier wave. To any human sensors watching only one planet in isolation, it looks like noise. To a distributed system spread across the solar system, it is a burst of data. None of this requires magic. We have already begun to use planets as parts of our own communication strategies, bouncing signals off atmospheres, considering how magnetospheres affect cosmic rays. The leap in the 3i Atlas scenario is simply scale and patience. Someone with a longer timeline might have seeded the outer darkness with receivers long ago, in places like Uranus's orbit, or even in the paths of objects like Bernardinelli Bernstein, waiting for the right alignment to light them up. December 19th then becomes not a random date pulled from a hat, but the next available window in a schedule that spans decades, the moment when all the pieces, including a newly radar-active Earth, line up in a way that makes a high bandwidth exchange practical. Back on our small planet, the significance of this is easy to miss. Calendar apps mark December 19th with ordinary reminders. Telescopes schedule their observations according to weather and proposal pressure, not according to ancient timetables written into interstellar missions. Space weather centers will watch the sun as they always do, issuing forecasts when they see coronal holes or flares that might disturb satellites and power grids. Even if the alignment subtly shapes one of those events into something a little sharper or stranger, it will still fit within the broad range of what the sun has always done. The cosmic clock will chime, and most of its audience will sleep through it. For the small community tracing 3I Atlas, however, the date has already begun to glow. They see the way the break has bent the trajectory into that narrow window. They see the opposition geometry and the way it drapes invisible structures across the inner system. They run simulations that, on paper, show how signals injected near the December 19th configuration can bounce and scatter in patterns that look suspiciously like a designed network. Officially, these are just models, just exercises. Unofficially, some of the people running them find themselves staring at the outputs longer than they mean to, wondering whether they are really predicting something or merely reconstructing a plan someone else made a very long time ago. As you lie here, the date may start to feel less like a point on a timeline and more like a doorway. It is still distant enough to be abstract, yet close enough that you can imagine waking up into it, checking the sky, scrolling past a headline about a moderate solar storm, and never knowing that somewhere far above you a grand exchange is underway. The question that floats at the edge of sleep is simple and unsettling. If December 19th is the moment when the solar system becomes, briefly, a piece of communication hardware for 3i Atlas and whatever waits beyond, are we part of that conversation, or are we only, once again, very small witnesses standing near the clock as it chimes for someone else? If you imagine sound carried not by air but by charged particles, the solar system becomes a place filled with a soft, continuous hiss. The sun breathes out plasma in all directions. Planetary magnetospheres deflect and shape that flow. The result, from a radio engineer's perspective, is interference almost everywhere, a storm of shifting static. Against that background, the idea that there could be a moment when the noise thins, when a particular route through the heliosphere becomes a little cleaner than usual, feels like wishful thinking. Yet when researchers took the new trajectory of 3i Atlas and laid it alongside models of the solar wind and the planetary fields, that is exactly what began to emerge, a temporary corridor in the turbulence, opening right around December 19th. The models were not mystical. They were the same tools used to forecast space weather for satellites and astronauts. Input the sun's current activity level. Add the positions of the planets. Solve the equations that describe how plasma and magnetic fields interact. Out comes a three-dimensional map of densities and field lines, color-coded for convenience. In most simulations, the inner system looks like a tangled nest of surfaces and spirals, a place where waves of charged particles collide and scatter. But in the runs centered on the Mercury-Earth-Uranus alignment, a pattern appeared. Along the line that connects those three worlds, there were intervals where the simulated turbulence dropped, forming what one analyst quietly called a low static lane. At first, this was dismissed as an artifact. Numerical codes can produce fragile features that vanish when you change a parameter. So they changed parameters. They nudged the solar wind speed up and down, altered the solar cycle phase, shifted planetary positions within their uncertainties. The exact shape of the lane wobbled, but it refused to disappear. Whenever the geometry put Mercury and Uranus in near opposition with Earth between them, a similar reduction in modeled turbulence appeared, like a faint groove worn into the heliospheric noise. It was never perfect silence. Space never offers that. It was simply quieter there than in the surrounding volume, quiet enough that a narrowband signal injected along the groove would suffer less scattering and absorption than one broadcast at a random angle. Grounded speculation turns that fragile feature into a piece of engineering. If you had an interstellar vehicle equipped with a limited power budget, but tasked with transmitting a very large amount of data to nodes scattered through the system, you would look for exactly these kinds of opportunities. You would time your main broadcast for moments when the natural environment helps rather than hinders you. December 19th, with its low, static lane stretching from the inner furnace near Mercury to the cold reaches around Uranus, becomes less a poetic date and more a scheduled opening in a complex, plasma-filled medium. The break that retimes 3i Atlas's arrival looks, in that light, like the cost paid to get a transmitter into optimal position before the lane is fully formed. There is another layer in the models that makes the timing feel even less accidental. When the simulations included realistic estimates of solar wind fluctuations, they showed that the low static lane does not stay open for long. As the planets move and the sun's own activity pulses, the corridor sharpens for a matter of hours to perhaps a day, then blurs back into the surrounding chaos. Arrive too early, and the fields are misaligned. Arrive too late, and the noise returns. The useful window is narrow. In mission planning terms, it is a launch window turned inside out, not for leaving a planet, but for injecting structure into the solar wind itself. To use it, 3i Atlas would need to be at the right place along its trajectory within a margin measured not in weeks, but in fractions of a day. The imaginative leap is to picture what happens during that brief interval if the object's systems are as capable as the break suggests. As it approaches the calculated point, the sunward jet that has been serving as a brake could change character, shifting from pure deceleration to a more complex exhaust pattern. Bursts of plasma and dust, ejected with precise timing and composition, would interact with the ambient flow, seeding the low static lane with disturbances that carry information. To distant receivers sharing the alignment, those disturbances would pass as subtle modulations in particle flux and magnetic field direction. To local sensors pointed elsewhere, they would look like an ordinary, if slightly unusual, solar wind event. The message would be steeped in the medium itself. Seen from Earth, the evidence for such a broadcast would be ambiguous by design. Space weather observatories might record an odd sequence of fluctuations, a storm that arrives a little earlier or later than expected based on visible solar activity. Magnetometers would twitch. Auroral cameras could capture curtains of light that ripple with an unusual rhythm. Analysts would file reports about an event that does not fit perfectly into existing categories. A few might notice that it coincided almost exactly with the moment 3i Atlas passed through its revised perihelion time. Fewer still would be in a position to connect that timing to the deeper pattern of the Mercury-Earth-Uranus alignment and to Forsitu, the 4-day break that made the overlap possible. From the perspective of whoever designed such a system, this ambiguity would be a feature, not a bug. Broadcasting openly on a single frequency invites attention and interference. Using the structure of the solar wind as a carrier hides the exchange and phenomena that every star naturally produces. Only a civilization that has mapped its own heliosphere in detail, that can predict and subtract the usual storms, would be able to notice the residue of an artificial pattern. If no such civilization exists, the message passes unnoticed, archived only in the quiet memories of machines waiting on distant orbits. If, however, there is a world like ours along the lane, a world that has begun to listen carefully, then the same event becomes both a test and an invitation. Overlay this on the human timeline, and the story takes on a different texture. Our radar ping on November 19th wakes the break, intentionally or not. 3i Atlas adjusts its path so that it will cross the low static lane at the moment it is most open. The weeks between are filled with small course refinements, invisible to the naked eye, but clear in the tracking data. On the ground, arguments continue about whether to treat the object as an ordinary comet, an oddity, or something that demands a new category. By the time December 19th arrives, the public narrative is still a gentle reassurance. The official position is that nothing dramatic is expected. Yet, in the background calculations, there is a quiet awareness that the alignment, the break, and the transmission window now occupy the same thin slice of time. As you lie here, you can let that slice stretch out in your imagination. A few hours in which the solar system's usual noise relaxes just enough to carry a structured disturbance from one edge to another. A visitor that has traveled for unthinkable distances eases into that moment like a ship sliding into a lock. Fields shift, particles surge. Somewhere near Uranus, and perhaps in other, more hidden locations, sensors light up and store the passing pattern. On Earth, the sky may brighten slightly near the poles. Instruments may register a storm that will be forgotten in a week. The window will close. 3i Atlas will drift onward, its break completed, its role as a transmitter fulfilled, or at least attempted. The question that remains, soft but insistent, is where we stand in this architecture. Are our sensors already good enough to see the difference between an ordinary storm and a message written in the wind, or will the transmission pass through our measurement logs as nothing more than an unusually pretty set of graphs? In the next section, as we follow 3i Atlas from transmitter to visitor, we will turn from the mechanics of the window to the meaning of the rendezvous itself, and to the unsettling idea that from the object's perspective, the real audience for December 19th might not be on Earth at all, but waiting elsewhere in the dark. When people first hear the words interstellar object and deceleration in the same sentence, the mind reaches for the simplest story. Something from the dark is slowing down near us, so it must be preparing to stop here, to hover near Earth, to attack. It is an understandable reflex. Our myths are full of spears and arrows that only slow when they hit a target. Yet the path of 3i Atlas, when you lay it quietly against what we know of weapons and ships, keeps slipping away from that fear. It is not behaving like a projectile that wants to do damage. It is behaving like something that is trying very hard not to. In the most brutal designs humans have imagined, a kinetic impactor is a simple creature. You give it as much speed as you can. You aim, and you let gravity finish the work. The energy it delivers when it strikes is proportional to the square of its velocity. Double the speed, and you quadruple the energy. There is no incentive to slow down, only to sharpen the trajectory. In that language, braking is waste. 3i Atlas has chosen the opposite path. Instead of letting the sun pull it into a deeper, faster dive, it has spent weeks bleeding away velocity with a sunward jet that behaves like a retro rocket. The deceleration is not dramatic enough to stop it, only enough to shift the date, tugging the closest approach away from the 15th and toward the 19th. That is a strange way for a weapon to behave. If you wanted to strike Earth or the Sun with maximum impact, you would drop the mask and fall as fast as gravity allows, perhaps even add your own thrust in the same direction. Every extra kilometer per second would make the eventual collision more devastating. Slowing down, especially by such a modest fraction, is an act of restraint, not aggression. The images and tracking data together form a quiet portrait of caution. The narrow, disciplined jet pointing almost directly toward the sun. The negative, non-gravitational term that appears in the fits as a small but persistent drag. The smooth way the predicted arrival date slides into its new position instead of lurching unpredictably. None of these are the marks of a system rushing toward impact. They look more like the routines of a pilot easing a heavy ship toward a crowded harbor, testing the thrusters, watching the currents, preferring to arrive a few days late rather than risk a fast approach that might go wrong. Grounded speculation follows naturally from that image. If 3i Atlas carries something valuable or fragile, whether that is physical cargo or stored information, then smashing into a planet or a star would be the worst possible outcome. A vessel built for delivery would treat the inner solar system not as a target, but as a delicate environment, full of small worlds and unstable fields. It would use its propulsion to control not only where it goes, but how quickly it passes through, much the way a freight ship approaching a port reduces speed far offshore to avoid tearing up docks or spilling containers. The brake, in that sense, is not the prelude to attack. It is a courtesy, a way of matching pace with a complicated stage before the main act begins. There is a quiet irony in how our fear misreads this behavior. We are used to thinking of threats as things that come at us faster than we can respond to. Missiles, flares, sudden storms. But in orbital mechanics, slowness can be a sign of care. When our own space agencies send vehicles to dock with the International Space Station, they do not roar in at full speed and then slam on the brakes at the last moment. They perform a long series of gentle maneuvers, matching orbits, trimming velocities, until the relative motion is almost calm. Only then do they make contact. They spend more fuel to move more carefully because they value what they carry and what they are approaching. The imaginative leap, in the case of 3i Atlas, is to picture it following a similar logic on a much larger and stranger stage. Its brake is not about fear or second thoughts, but about matching itself to an invisible timetable and environment that we have only begun to detect. Perhaps there is a specific patch of space near the December 19th transmission window where fields are smoother, where the low static lane we saw in simulations bends just so, where the risk of disrupting its own outgoing signal or damaging a receiving structure is minimized. To hit that patch too fast would be to waste decades of planning. To arrive exactly on time at a controlled speed is to respect a design that might span the orbits of multiple planets and the lifetimes of entire civilizations. This interpretation also casts a different light on the way 3i Atlas treats Earth. If it were an impactor, our planet would be the bullseye, the place toward which the trajectory is gradually tightened. Instead, Earth sits off to the side of the main path, near enough to observe but not in the crosshairs. The adjusted orbit does not curve in to meet us. It curves to meet a schedule, a configuration, a window. The energy budget is spent on aligning with December 19th and the Mercury-Earth-Uranus line, not on narrowing the missed distance. To a pilot focused on delivery, we are not the target. We are part of the scenery, an audience member seated close enough to feel the vibration of the passing ship, but not so close that we are at risk of being struck. There is, of course, a more unsettling variant of this same picture, one that rides beneath the calmer reading like a darker current. It is possible to imagine a system that arrives gently not out of kindness, but out of technical necessity. A vessel might need to decelerate in order to deploy devices, release capsules, or interact with existing hardware scattered through the system. In that case, the brake would still be serving delivery, but the nature of what is being delivered could range from benign knowledge to something more invasive. A network of probes waking up in the orbits of asteroids. Seed packages aimed at future waypoints like Apophis or Bernardinelli Bernstein. From a distance, we would see only the deceleration and the timing, not the contents of the hand that moves through the dark. Even in that darker version, however, the physics tells us something important. A kinetic weapon that relies on raw impact does not need elaborate alignments or narrow bandwidth windows. It does not care about low static lanes or Mercury-Uranus opposition. It wants speed and mass and an uncorrected fall. As long as 3i Atlas continues to behave like a craft that prioritizes timing over impact, the argument for invasion remains thin. The stronger story, whispered by the way it breaks and by the way it steers toward a complex configuration, is one of delivery and exchange, of some kind of interaction that happens through fields and signals rather than through craters. For the people watching from Earth, this shift in interpretation is both comforting and disorienting. It is easier, in a way, to imagine a clear threat you can point to, something that either hits or misses. It is harder to contemplate a delivery whose contents are unknown, whose recipients might not even be on our world. We are used to being the main characters in our stories. 3 Atlas suggests a narrative where we might be present at the event, close enough to watch and to measure, but not central to the purpose. We may be bystanders standing at the edge of a landing zone meant for someone or something else. As you lie here, you can let that possibility settle over you like a quiet sea. Somewhere out there, a long-traveled craft is slowing not to strike, but to align, pacing itself against a clock made of planets and magnetic fields. It is treating the inner solar system as a place to be navigated with care, not a target to be broken. The break is its way of matching step with a rendezvous that was planned long before we pointed a radar dish at the sky. The question that follows, gentle but persistent, is no longer what it intends to do to us, but what and who it intends to meet. In the next part, we will turn directly toward that question, leaving the mechanics of delivery behind and asking, as honestly as we can, who the true recipient of this careful, decelerated arrival might be. There is a temptation, whenever we talk about messages in space, to assume that we are the addressee. The moment we see patterns, alignments, or decelerations, we place ourselves at the center of the story. If 3i Atlas is breaking, then it must be breaking for us. If there is a window on December 19th, then it must be a show for Earth. But when you look carefully at the geometry of the rendezvous and the cost of the break, another, quieter possibility emerges. We may not be the recipient at all. We may be holding the camera while someone else receives the letter. Think first about proximity. From our point of view, 3i Atlas will pass through the inner solar system at a respectful distance, close enough for detailed observations, far enough that no one has to write evacuation plans. The trajectory does not narrow toward Earth with the ruthless focus of a targeted mission. Instead, it threads a path that seems more loyal to the alignment of planets and fields than to any particular world. If you draw the revised orbit on a map of the system, the closest approach flows along that Mercury-Earth-Uranus bar, skimming through the low static lane we traced earlier. Earth is near that line, but off to the side, like a person standing close to a railway, watching a train that will not stop at their station. Then consider the energy budget again. The brake spends fuel to move the date of arrival, not to shrink the distance to any planet. That is a strange choice if your goal is to deliver something directly to a surface. For a probe aiming at Earth, Apophis, or any specific target, the most efficient strategy would be to adjust the trajectory so that the object itself passes closer and to let the timing fall where it may. Instead, 3i/Atlas prioritizes time over distance. It seems more important to be present during the December 19th configuration than to be physically near any one body. That is the behavior of a transmitter serving a network, not a courier delivering a package to a particular doorstep. Grounded speculation points to three broad candidates for the true recipient. The first is the obvious one, Earth. Even if the object does not aim to collide with us or orbit us, it might still be timing its passage to coincide with our technological readiness, using the low static lane as a way to push a signal into our magnetosphere with minimum loss. We have the instruments to notice unusual storms and spectrograms. We have already, perhaps, triggered the rendezvous by pinging it with radar. In that scenario, the main transmission on December 19th is for us, whether we recognize it or not. The second candidate lies further out, in orbits that sound familiar but rarely feel personal. Apophis, for example, is a near-Earth asteroid with a well-known close flyby in 2029. Bernardinelli Bernstein is a giant comet creeping inward on a path that will bring it close to the outer planets in the coming decades. In previous stories on this channel, they have been treated as looming presences, future waypoints where larger arcs might intersect. From the perspective of 3i Atlas, both objects have something in common. They are massive, long-lived, and follow predictable paths. If you wanted to seed the solar system with devices or archives that will persist for centuries, those are attractive homes. It is not difficult to imagine that somewhere within their cold interiors, dormant receivers or processors could be waiting for a very specific pattern to wash over them on a particular date. The third candidate is not a single object, but the architecture of the system itself. The recipient could be the distributed network of probes, stations, or modified bodies that we have not yet recognized as anything but rocks and ice. In that view, December 19th is the moment when a long silent network checks in, using the solar wind and planetary fields as cables. 3i Atlas is only the local node that initiates the burst. The true recipients could be sprinkled across orbits we barely monitor, from Trojan clusters to Kuiper belt objects. We would see only the initiating node and the ripples. The real conversation would unfold somewhere beyond our telescope's current attention. The imaginative leap is to picture each of these possibilities in turn, to see how the break and the rendezvous would look through their eyes. If Earth is the intended listener, then December 19th might bring subtle but detectable anomalies in our space weather data, patterns that repeat across different instruments and latitudes in a way that is hard to explain with ordinary solar activity. Perhaps a specific sequence of fluctuations appears in magnetometer logs around the world, the same motif written into different traces. Maybe certain radio bands experience structured fading or enhancement, like the ghost of a code pressed across multiple channels at once. The challenge would be to distinguish that motif from the millions of other patterns streaming through our sensors every day. If Apophis is part of the design, the picture shifts forward in time. The transmission blaze on December 19th could be aimed partly at updating devices embedded in that asteroid's interior, sending new instructions or data that will only be acted upon when Apophis swings close to Earth in 2029. In that scenario, 3i Atlas is not just talking to the present. It is sending a note to the future, one that will ride inside a rock we already plan to study closely. Our own missions to Apophis might then find anomalies in its structure, strange cavities or materials that do not match its expected composition. We would interpret them as peculiar geology unless we have already learned to read them as parts of a system. For Bernardinelli Bernstein, the timescale stretches even further. A broadcast timed to coincide with a particular inner system alignment could carry updates or triggers for systems embedded in that giant comet, waiting to wake when it reaches certain distances from the sun decades from now. It is an unnerving thought that the real upgrade is happening not near us, but in a distant ice mountain that will not visit our neighborhood for many human lifetimes. From that perspective, our radar ping on November 19th and the break that followed might have been of secondary importance, a minor branch in a long-running maintenance protocol. We heard a whisper of a much larger process that is mostly indifferent to us. There is a darker, more intimate variant of the network idea too. If the solar system has been quietly instrumented over long timescales, the true recipients could be devices hidden in places we consider protected. Deep under the surfaces of moons, inside the rubble of captured asteroids, even within the gravitational wells of planets themselves. They would not need to be large. A handful of machines scattered through a system can reconstruct a complex message if it is written into the dynamics of the environment. In such a case, we might already be sharing our orbit with listeners that do not care whether we notice them. December 19th would be their check-in, their firmware update, their reminder that the network still exists. Amid these possibilities, one question keeps returning with a kind of quiet insistence. If we are not the primary recipient, why did 3i Atlas answer our radar ping at all? Why allow a narrow 2.4 gigahertz line to appear in the spectrogram where our instruments could catch it? One grounded answer is that the transponder protocol does not distinguish between primary and secondary audiences. Any emergent technological species that manages to ping the craft gets a simple acknowledgement, a way of saying that their presence has been registered. The real payload, however, is reserved for the larger network, delivered through windows like December 19th that have nothing to do with our calendars and everything to do with the slow choreography of planets and debris. The imaginative twist that may be hardest to accept is that in this architecture, we occupy a role somewhere between bystander and junior partner. We are close enough and advanced enough to notice the anomalies, to see the break, to record the spectrograms. We are not yet central enough to be written into the heart of the rendezvous. From Three Eye Atlas's perspective, we might be like villagers watching a fiber optic cable being laid through their town, aware that something important is happening, even able to tap into it a little, but not the reason the cable was built. That does not make us irrelevant. It simply means that the story is bigger than us. As you lie here, this shift in perspective can feel both humbling and strangely comforting. The idea that not everything in the sky is about us can take some of the sting out of our fears. If Three Eye Atlas is delivering an update to a network that spans Apophis, Bernardinelli Bernstein, Uranus, and places we have not yet named, then our role may be to observe, to learn, and to decide how to respond, rather than to brace for impact. The question that lingers, soft and unresolved, is what we do with that knowledge. Do we try to insert ourselves into the conversation, sending more pings, broadcasting our own patterns into the low static lanes of gaze when they open? Or do we accept, for now, that we have stumbled into watching someone else's rendezvous, and that our wisest move may be to listen as carefully as we can before we decide what to say back? In the final part, we will pull back one more time, watching Three Eye Atlas drift toward its December 19th appointment, and then beyond it, and we will sit with the long, quiet waiting that follows. The sense that what matters most may happen not in a single burst of drama, but in the slow unfolding of what we do after the break has finished its work. In the end, the story of Three Eye Atlas is not a single moment of revelation, but a slow, deliberate rearranging of how we think about visitors from the dark. By the time December 19th approaches, the facts are simple on paper. An interstellar object entered the solar system. It displayed a measurable deceleration anomaly, a break that nudged its arrival 4 days later than gravity alone would allow. A narrow, sunward jet mimicked a retro rocket. A radar ping coincided with a strange 2.4 gigahertz line. The predicted close approach slid into alignment with a rare configuration of Mercury, Earth, and Uranus, opening a low static lane through the heliosphere. All of that can be written into reports and archived. What does not fit so easily into tables is the feeling those facts leave behind, like a faint pressure at the edge of thought. In the days leading up to the rendezvous window, telescopes around the world track Three Eye Atlas as best they can. It remains a dim, unresolved point, its coma soft and unthreatening, its brightness variations almost lazy. To casual observers, it looks no more menacing than any other comet that has ever slipped past the sun. There is no glare, no monstrous silhouette growing in the sky. The sense of significance lives instead in the timing. Each nightly update from the orbit fitters confirms that the break has done its work. The uncertainties tighten, the date holds. December 19th settles into place as if it had been there from the beginning, waiting for us to notice. Inside control rooms and small research groups, the mood is quieter than the public might imagine. There are no cinematic countdowns, no red lights. Instead, there are overlapping schedules of observations, scripts prepared for satellites and ground-based instruments to record whatever the sun and the solar wind choose to do that day. Some teams focus on 3i Atlas itself, tracking its position, its faint spectrum, any subtle changes in the orientation of its jet. Others point their attention at the sky around it, at the broader space weather patterns threading along the Mercury-Earth-Uranus line. A few, influenced by the same whispers that have guided this story, design their analyses to look not just for storms, but for patterns inside storms. From the outside, none of this is visible. For most of humanity, December 19th arrives like any other winter day. People go to work, to school, to late-night shifts. In some regions, holiday lights are strung across streets, reflecting off windows while the sun traces its low arc. Weather on Earth obeys its own chaotic rules. News feeds show familiar topics. If an article about an interstellar comet nearing its point of closest approach appears at all, it is a small piece framed as an interesting but remote event, something you might scroll past on your way to more immediate concerns. The idea that the solar system is about to serve as a temporary transmission device for a long-traveled craft does not make it into the headlines. And then, in the models, in the magnetometers, in the faint signals recorded by instruments that most people do not know exist, the window opens. The low static lane through the heliosphere sharpens as Mercury, Earth, and Uranus hold their brief configuration. 3i Atlas glides into its revised perihelion time, the break finished, its velocity but now exactly what its guidance system has prescribed. If there is a main transmission, this is when it happens, not as a single blinding flash, but as a subtle reshaping of existing flows. Plasma waves crest and break in patterns slightly different from the forecasts. Magnetic field lines ring with a sequence of twists that, to the right decoder, might spell out a long delayed report or instructions. On Earth, the signs are small and easily folded into ordinary explanations. Space weather centers notice an event that is a little out of character for the visible state of the sun, perhaps a mild storm with an unusual temporal structure. Satellite operators receive routine advisories, switch certain systems into safe mode for a few hours, and then resume normal operations. High-latitude skies may host auroras that flicker with an oddly regular cadence, curtains of green and violet that ripple in a rhythm some cameras capture, but no one thinks to translate. Somewhere deep in their logs, instruments store the shapes of those fluctuations, waiting for someone, years from now, to wonder whether they were only noise. Far from Earth, along orbits we have barely begun to explore, other events unfold that we may never witness directly. A buried device inside a small asteroid wakes for the first time in centuries, processes the passing disturbance, and quietly updates its memory before going back to sleep. Something hidden in the frozen strata of a distant comet shifts its internal state by one tiny step, moving closer to a threshold it will not cross until long after our lifetimes. Perhaps a network of microscopic machines drifting in the outskirts of Uranus's magnetosphere receives a packet of structured changes in particle flux and redistributes them along paths we have not mapped. The rendezvous that 3i Atlas has worked so patiently to keep is not a single meeting in a single place. It is a coordination across space and time, a quiet rehearsal for futures we have not yet joined. Through all of this, the object itself remains almost anonymous. Observers record that the sunward jet appears to shift, its intensity changing in ways that may indicate the end of the main braking sequence. The non-gravitational term in the orbit fits begins to relax. The trajectory, now retimed, flows onward, carrying 3I Atlas out of the inner system and back toward the interstellar space. Whatever main role it had to play in this system seems to have been completed in the same way it began, gently, efficiently, without spectacle. The ship, if that is what it is, does not linger. It passes through its appointed slot in the cosmic clock and then drifts toward the next one, leaving behind only altered fields and data files on distant servers as proof that anything unusual happened at all. In the weeks that follow, life on Earth settles back into its usual mixture of urgency and forgetfulness. Papers are written about the deceleration anomaly, about the peculiar outgassing pattern, about the modest but real shift from a December 15th to a December 19th perihelion. Some of those papers hint, in careful language, at controlled behavior. Others stick closely to natural models. Conferences host quiet hallway conversations where the words probe and mission are used more freely than in any official talk. But outside those circles, 3I Atlas fades from view. New stories take its place. New crises demand attention. The strange visitor becomes another entry in catalogs and databases, remembered mainly by those who kept watch as it passed. For you, lying in the dark with this story still moving softly through your thoughts, the great waiting begins after the rendezvous, not before it. Because the real weight of the break is not in what it might have delivered, but in what its existence implies. If an interstellar object can adjust its arrival time to match planetary alignments, if it can answer a radar ping with a line in our own noisy band, if it can treat the solar system as a piece of infrastructure rather than a random obstacle, then we have to live with the possibility that this has happened before and will happen again. The 19th of December becomes not an endpoint, but one chime in a clock that has been striking without us for a very long time. And yet, best yet, there is comfort in that realization. It suggests that we are not living at the edge of a sudden catastrophe, but at the edge of a much older conversation that we are only beginning to overhear. 3I Atlas did not slam into our world. It did not hover ominously overhead. It performed a careful, mathematically honest maneuver to arrive at a window that aligned with physics, not with fear. Whatever it delivered, if anything, it did so through fields and particles, through structures that do not tear planets apart. We were, at worst, bystanders standing near a line of communication we did not build. At best, we were quiet participants, our radar ping on November 19th serving as a small, earnest wave that the craft acknowledged before proceeding with its work. So you can let the image settle now. Out there, beyond the reach of naked sight, 3I Atlas is already receding, its sunward jet gone, its path bending gently away into the dark between stars. In your mind's eye, you might still see it as a machine, wrapped in the guise of a comet, drifting in silent afterglow after a long, careful braking burn. Behind it, the solar system relaxes. The low static lane dissolves back into ordinary turbulence. Magnetospheres resume their usual dance. On Earth, the auroras fade, and the instruments keep recording, as they always do, waiting for the next anomaly that will make someone look twice. If this was a delivery, we may not yet know what has been left for us, or for others. If it was a test, we have at least passed the first part by noticing that something strange was happening at all. The great waiting is the space between that noticing and whatever we choose to do next. Do we send more deliberate calls, crafted and patient, into the places where the static wears thin? Do we comb our archives for patterns and around other dates and other alignments, searching for echoes of transmissions that came and went before our instruments were ready? Or do we simply lie here for a while longer, listening to the soft rush of our own planet beneath us, aware that the sky above is full of trajectories and timetables we have only just begun to see? For tonight, it is enough to know that not every visitor from the dark is a harbinger of impact. Some arrive like couriers, slowing not to strike, but to keep an appointment written into the fabric of orbits and fields. Some burn their fuel not to hurt, but to be on time. As sleep comes, you can let Three Eye Atlas drift to the edge of your awareness, a small, precise question mark moving out into the stars. The rendezvous of December 19th will pass, the data will settle, and the universe will go on being vast and quiet. Somewhere in that quiet, the memory of a single patient break will remain, a reminder that the next time an object bends the laws of falling just a little, it might not be a threat, but an invitation.